For millennia, humans have gazed up at the night sky, filled with awe and wonder. From the earliest civilizations to modern times, the stars have been a source of inspiration, mystery, and deep curiosity. They've guided travelers, inspired myths, and sparked some of the most profound questions ever asked. The stars, like celestial diamonds scattered across a velvet canvas, have sparked countless questions about our place in the vast expanse of the universe. What lies beyond them? Are we alone? How did it all begin? These questions have echoed through time, passed down from generation to generation. Where are we in this grand cosmic dance? Are we merely spectators, or do we play a more significant role in the unfolding story of the universe? What is our role in this intricate tapestry of celestial objects? These questions have driven humanity to build tools, develop theories, and explore the unknown in search of answers. It's a question that has captivated philosophers, scientists, and dreamers alike for centuries. From Aristotle to Galileo, from ancient skywatchers to modern astrophysicists, the quest to understand our place in the cosmos has never ceased. One of the earliest and most enduring answers to this question placed Earth at the center of it all. This idea wasn't just scientific, it was philosophical, spiritual, and deeply human. This idea, known as geocentrism, dominated astronomical thought for over 1,000 years, shaping our understanding of the cosmos and our place within it. It was a worldview that made sense of the heavens using the tools and knowledge available at the time. Imagine a time when the Earth was considered the unmoving heart of the universe, with the sun, moon, planets, and stars all revolving around us. This model offered a sense of order, purpose, and even comfort. It placed humanity at the center of creation. This was the prevailing belief for much of human history, a testament to the power of observation and the limits of our early understanding. It was a model built on what could be seen with the naked eye, interpreted through the lens of culture and belief. But as our tools for observing the heavens improved, so too did our understanding of the universe. The invention of the telescope opened up a new window to the cosmos, revealing details that challenged long-held assumptions. The geocentric model, once a seemingly unshakable truth, began to crumble under the weight of new evidence. Observations of planetary motion no longer fit the old model, and a new idea began to take shape. What emerged from this scientific revolution was a radically different view of our place in the cosmos, one that dethroned Earth from its central position and cast the sun as the gravitational anchor of our planetary family. It was a humbling shift, but also a liberating one, opening the door to a universe far more vast and wondrous than we had ever imagined. The idea of a geocentric universe, with Earth as the central point around which all celestial objects revolve, has deep roots in human history. For thousands of years, people looked up at the sky and saw a grand cosmic dance unfolding above them. The stars, planets, sun, and moon all appeared to move in perfect harmony around a seemingly still Earth. In a world where the ground beneath our feet feels solid and unmoving, and where we experience no sensation of motion, while the sun, moon, and stars trace predictable paths across the sky day after day and night after night, it's easy to understand why early civilizations believed Earth must be at the center of it all. After all, our senses seem to confirm that we are stationary, grounded, and at the heart of the universe's motion. The heavens, in contrast, appear to revolve around us in a majestic, orderly rhythm. The ancient Greek astronomer Ptolemy, who lived in the 2nd century AD, took this intuitive idea and gave it structure. In his monumental work, the Almagest, he formalized the geocentric model into a comprehensive system. Ptolemy's model wasn't just a philosophical idea, it was a detailed framework that explained the apparent motions of the heavens. It was a sophisticated mathematical system, complete with calculations and tables, that allowed astronomers to predict celestial events. The model used a series of circles, epicycles, and deferents to account for the complex paths of the planets, especially their retrograde motion. Imagine trying to map the movements of the planets without the aid of telescopes or modern technology. The precision and creativity involved were extraordinary. Ptolemy's model, with its intricate system of epicycles and deferents, was a marvel of ancient science. It demonstrated how far human reasoning could go in explaining the cosmos using only observation and logic. For over 1,000 years, Ptolemy's geocentric model reigned supreme, taught in schools and accepted by scholars across continents. It shaped humanity's understanding of the universe, placing Earth at the center of a grand, ordered system. The model aligned with religious and philosophical beliefs of the time, reinforcing the idea of a purposeful, human-centered cosmos. It seemed to fit with our everyday experience, where the sky moves and we do not. And it provided a sense of harmony and structure to the universe, a cosmic order that mirrored the order people sought in their lives. However, as with all scientific theories, the geocentric model was not immune to scrutiny. With the invention of the telescope and the rise of new thinkers, the model began to show cracks. New observations and revolutionary ideas would soon challenge the geocentric worldview, setting the stage for a cosmic transformation. While Ptolemy's geocentric model held sway for centuries, it wasn't without its critics. As early astronomers continued to observe the heavens, they noticed certain phenomena that didn't quite fit with the Earth-centered view. For example, the planets sometimes appeared to move backwards in their orbits, a phenomenon known as retrograde motion. This was difficult to explain if the planets were simply orbiting Earth in perfect circles. To account for these discrepancies, astronomers added more and more epicycles to the geocentric model, making it increasingly complex and cumbersome. Imagine trying to explain the movement of a car by saying it's attached to a series of invisible ropes, each pulling it in a slightly different direction. That's what the geocentric model was starting to resemble. The first cracks in the geocentric edifice began to appear in the 16th century with the work of Nicolaus Copernicus, a Polish astronomer who dared to challenge the prevailing wisdom. Copernicus proposed a radical alternative, a heliocentric model, with the sun at the center of the solar system and the Earth revolving around it, just like the other planets. This revolutionary idea would forever change our understanding of the cosmos. Nicolaus Copernicus, a Polish astronomer working in the 16th century, is credited with sparking the scientific revolution that shifted our understanding of the cosmos from an Earth-centered to a sun-centered system. At a time when the geocentric model, which placed Earth at the center of the universe, was deeply entrenched in both scientific and religious thought, Copernicus dared to challenge centuries of accepted wisdom. His revolutionary ideas laid the groundwork for a new era of astronomy and fundamentally altered humanity's place in the cosmos. His heliocentric model, published in his book De Revolutionibus Orbium Coelestium, or On the Revolutions of the Heavenly Spheres, in 1543, placed the Sun at the center of the solar system, with Earth and the other planets orbiting it in circular paths. This was a bold departure from the Ptolemaic system, which had dominated astronomical thinking for over 1,000 years. Copernicus's work was not just a scientific proposal, it was a philosophical shift that questioned humanity's central role in the universe. Copernicus's model, while initially met with resistance, offered a simpler and more elegant explanation for the observed movements of the planets, including the perplexing retrograde motion that had puzzled astronomers for centuries. In the geocentric model, retrograde motion required complex systems of epicycles, small circular orbits layered on top of larger ones, to explain why planets appeared to move backward in the sky. The heliocentric model eliminated the need for these convoluted mechanisms. By placing the Sun at the center, Copernicus was able to explain retrograde motion as an optical illusion caused by the relative motion of Earth and the other planets as they orbited the Sun. When Earth, moving faster in its orbit, overtakes another planet like Mars, that planet appears to move backward temporarily against the backdrop of distant stars. This insight was a major breakthrough in understanding planetary motion. Imagine two cars traveling at different speeds on a highway. From the perspective of one car, the other car might appear to be moving backward, even though it's moving forward. This analogy helps us grasp how relative motion can create the illusion of reversal, just as it does in the night sky when we observe planets from our moving Earth. Copernicus's heliocentric model was further refined and supported by the observations of Galileo Galilei, who used the newly invented telescope to observe the phases of Venus, the moons of Jupiter, and other celestial phenomena that provided further evidence against the geocentric model. Galileo's discoveries were groundbreaking. The moons of Jupiter, for instance, clearly orbited a body other than Earth, challenging the idea that everything revolved around us. The phases of Venus, which could only be explained by a sun-centered system, offered direct observational proof of Copernicus's theory. The work of Johannes Kepler, a German astronomer, further solidified the heliocentric model by showing that the planets orbit the Sun in elliptical paths, not perfect circles as previously believed. Kepler's laws of planetary motion corrected the inaccuracies in Copernicus's circular orbits and brought mathematical precision to the heliocentric theory. His insights were based on meticulous observations and calculations, particularly those of the planet Mars. Kepler's laws of planetary motion accurately described the motion of the planets and paved the way for Isaac Newton's law of universal gravitation, which explained the force that holds the planets in their orbits around the Sun. Newton's work unified the heavens and the earth under one set of physical laws, completing the transformation that Copernicus had begun. What started as a radical idea in a modest manuscript became the foundation of modern astronomy and forever changed how we see our place in the universe.